Scalars. Here we're going to look at different quantities, some of the different quantities that are considered scalar quantities, which are different from vectors, and we'll get those later on. A scalar is a quantity that has only size, but no direction. So when we say size, that's known as magnitude. This is the value, a numerical value attached to the quantity or measurement. These almost always include units, but there's no direction for a scalar. Time is a scalar quantity. It has no direction, but it does have magnitude, and it also has units. Here are some other examples. Distance is also a scalar. Speed, as previously mentioned, time, and also frequency, and frequency is one that we'll see later on when we talk about waves. Work, which is related to energy, and any kind of energy is also a scalar, so potential energy and kinetic energy are scalars. Voltage, current, and resistance, and a number of other electrical quantities are also scalar quantities, and there are many more. But these are the ones that we're going to see in this course for the most part. Let's try adding some scalars. Ms. Roseberry walks 2 meters north and 1 meter south. What's the total distance that she walks? Well, since these values are scalars, distance is a scalar, we do not incorporate her direction. So it doesn't matter that she traveled north for part of her trip and then south for the other part. We just add the magnitudes. So direction doesn't matter. It's just 2 meters plus 1 meter for a total of 3 meters for her total distance. If we want to find the average speed for an object, then we divide the distance traveled by the time, which looks like this. So speed has units of distance over units of time. Usually we will use meters per second, although for drivers, they'll be more used to kilometers per hour. Those are the two most common units, or sets of units, for average speed. And like distance, of course, average speed is a scalar, because we're dividing a scalar by a scalar. Let's try an example. Matt runs 180 meters in 0.75 minutes. What is his average speed in meters per second? Well, Gus would write down the given values first, so that's what we'll do. Distance is 180 meters, time 0.75 minutes, and our unknown is average speed. We'll convert the time, because we want to get meters per second for our units in the ends, which means we need time given in seconds. So 0.75 minutes times 60 seconds per minute gives us 45 seconds. Using our average speed formula, so delta D over delta T, we've got 180 meters divided by 45 seconds, or 4.0 meters per second. We can also rearrange the equation for average speed to find distance or time. So if we solve for distance, our equation becomes delta D equals average speed times delta T. If we solve for time, then the equation becomes delta T equals delta D, distance that is over average speed. Sometimes we give distances using units of time, which is incorrect, as far as physicists are concerned, but is something that happens in conversation between people quite often. For example, how far is McMaster? 10 minutes, we might say. We're describing the distance using the time that it would take us to get there. We're making some assumptions there. We're assuming that we're traveling at the speed that we would normally have traveling in a motor vehicle. 10 minutes to McMaster. If we walked everywhere, then we would describe it differently. How far is Megan's run? If Megan is running at 4 meters per second, how long will it take her to run a 5-kilometer trail? Again, we'll write down the given values. Average speed is 4 meters per second. Distance is 5 kilometers, but we'll convert that to meters, so 5,000 meters. Unknown is the time. We know average speed equals distance over time. And so we'll rearrange to get time by itself, because we want to get the unknown by itself. So delta t is equal to distance divided by speed. So time is equal to 5,000 meters over 4 meters per second, or 1,250 seconds, which is about 20 minutes when we convert. Sometimes we want to know the instantaneous speed of an object, which is different from the average speed, although depending on the situation, they might have the same magnitude. Here we can assume that Megan was running at a constant speed of 4 meters per second, but was Matt running at a constant speed of 4 meters per second? Not necessarily. His instantaneous speed at any moment in time might have been different from his average speed. So he might have had a speed of 0 at the start, for example, and he may have sped up and slowed down and changed his speed a number of times, which means that his instantaneous speed was changing. Let's say Ms. Roseberry walked 3 kilometers at a constant speed of 1.5 meters per second, and another 1 kilometer at a constant speed of 1 meter per second. What was her instantaneous speed at the first 1 kilometer mark? And then her average speed for the entire walk. Well, she's still walking the first 3 kilometers, so she's walking at 1.5 meters per second. We know that in the first 3 kilometers her speed is constant. So that answers part A. Part B, what's her average speed for the entire walk? Well, it's not 1.25 meters per second, because we have to look at the total time and the total distance when we're finding average speed. So let's have a look at that. So to find the total distance, we'll need the distance that she travels in the first part of the trip, and then we'll add the distance that she travels in the second part of the trip. So 3,000 meters plus 1,000 meters is a total of 4,000 meters. The total time, well, time is equal to the distance that she travels over her speed, and so we'll do that into 2 parts. So here's the time that she takes to do the first part of the trip, and here's the time that she takes for the second part of the trip. So 2,000 seconds plus 1,000 seconds, which is 3,000 seconds. Now that we have those 2 values, we can divide the total time by the total, the total distance by the total time, and we get 1.3 meters per second for her average speed, using those values for the entire trip. And now you can get a little bit more practice.